recording so I don't forget. And welcome everybody formally to this November webinar of the Chemistry Education Research Group. This webinar is by Scott Lewis from the University of South Florida. He's in the chemistry department there. Those of you who know Scott know he's interested in lots of different aspects around education, research, and chemistry, things like looking at curriculum effectiveness, student study habits, peer-led team learning, and so on. Those of you who've heard him speak or read his work will know that there's a real sense of impact with his own students. It's something I always get from his work, that he's not just sharing with other people, you really get a sense of impact with his own students. And then it's no surprise when you read his CV to see he's won lots of teaching awards, including those at his own institution now, where he's won the University Undergraduate Teaching Award from the Chemistry Department, and so on. And I think that's really clear to us as external observers. It's a real hallmark of his work. There's a real impact with his own students. He also serves the community by being editor of Chemistry Education Research and Practice, that fine journal. And before I pass over to Scott, I will just say thank you to Learning Science, who have sponsored this webinar, and their sponsorship will go towards supporting the Chemistry Education Research Group's mentoring scheme that's going to start next year. So I'll remind the audience as Scott is speaking just to prompt in any questions as you can, as you think of them. But for now, Scott, we're very excited. Thank you very much for joining us in this webinar, and I'm really looking forward to hearing your talk. So I'll pass it over to you.
Well, thank you, Michael. Thank you, everybody, for joining us today. I'm really excited to get this opportunity. So jumping into the project, title is At-Risk Students in Equity in Post-Secondary Introductory Chemistry, and equity is going to be a big focus, and I'm going to talk about it in two different studies. But I'd like to begin with kind of an impetus for this work. And so I've got here a Sankey diagram. And on the left is student scores on what's called the SAT. It's an aptitude test that students take in secondary school or in high school as they approach applying for colleges and universities. So a lot of colleges and universities use this test to determine things like admissions, placement, those types of things. And so on the left, we've demarcated it by quartile. And at the top, it says at-risk students up here. So that would be the bottom quartile, the students who scored in the bottom 25 percentile. And then as you go down, you can see the higher and higher quartiles till you get to the top quartile. And on the right is the students' final grades in introductory chemistry or general chemistry. So the width of the bar that connects the two indicates the proportion of students that ended up receiving that grade. And it can take some time to study it. It's a fascinating diagram, and you can kind of explore it. But focusing on the at-risk students, one of the things we see is that it's a very narrow bar that ends up with the highest grade of an A. And then from there, we see wider bars for B. And if you take a look at C, nearly half the students who get a C in the course came from this at-risk cohort. And then down here, same with the DFW, the students who did not succeed in the course, they came from the at-risk students. And for us, this is a concern, because when you've got a metric that happened before the semester even began, and it's informing us that students are not succeeding in the course, that means that our course is not designed in a way that all students can succeed. And we would like to find a way to address that. Now, I know SAT is a US-centric measurement, so I'm hoping that people and an international audience could think of other factors in their course that they have witnessed relating to performance in the course, and think about student groups from that metric that may not be succeeding at such a high rate as everybody else, and what they can do to address that. And I think in this talk today, I'm going to present a couple studies that show some lenses in terms of how we understand it. But before I get into that, let's do a quick framework for equality, equity, that kind of thing. And we've been using Sharon Lynch's framework. It's a great book. It came out in 2000, and she breaks down equity as part of, where equity can be framed in three different lenses, I guess is the way I would describe it. The first lens is equality of output, and this is where the students who succeed in the course match the demographics of the students who enter the course. So there would be no difference between looking at characteristics of them entering the course and the characteristics of the successful students. And that would be the goal if you've got a science for all type framework, that you want to see those incoming characteristics not affect their success in the course. The second one is equality of inputs, and this might be a more conventional way that you would think of equity as a teacher, in that everybody must be treated the same. And so whatever I do, everybody's going to get the exact same experience. And what Sharon Lynch argues is that when we have that framework, we're not going to achieve equality of output, because we've looked at enough characteristics like I just showed in the Sankey diagram where equality of output is not being achieved while we strive to maintain equality of inputs. So Sharon Lynch advocated for what she called equity as fairness, where we consider a trade-off in resources that departs from equality of inputs but strives to achieve equality of output. One of the ways you might frame this is you might think to yourself, well, if I lecture in my course the whole time, everybody's getting the same lecture, that I'm achieving my equality of inputs. But lecture doesn't work equally for all students. Some students are more accommodated to it. Some students have more experience with it, and they're going to succeed at a disproportional rate if that's your sole instructional strategy. So equity as fairness would ask you to come in and think about what changes could you make that could be more inclusive of all the students in your class. You may have heard of differentiated instruction. This would be an example of that, where you're trying to promote success for the different groups, recognizing that not one technique is going to work for all students. So a little bit about the research setting. We're focused on General Chemistry 1. This is the first chemistry course that students would take at the university level. It's done in a large class environment with class sizes of about 250 students. The class meets in a lecture twice a week for about 75 minutes, and once a week they have a problem-solving session with peer leaders. And the class is coordinated, so they use a common syllabus. They cover the same content across several classes that run concurrently, and they all take the same exams at the same time. A little bit about the grading. So there's 3 exams that we run throughout the semester at 15% each, the final exam 25%, 8 online homework assignments that are 10%, attendance to those problem-solving sessions are 10%, and the lectures are supported with in-class clicker use, and that's also accounting for about 10% of their grade. Now in this first study I wanted to talk about, one of the things that we tried to understand is, where do the at-risk students struggle? What is the nature of their struggles in this, among this cohort? And one of the first things that happened was a graduate student working with me, Vanessa Ralph, coded a bunch of items based off of their topics. And we started with an open coding scheme, assigning them to different topics, refining the topic list. And I'm really kind of giving an abbreviated version of the coding right here, but it ended up with these 16 topics, and they're organized in the order that they're presented in class. Now, I'm not going to spend a lot of time on it, but it's kind of a conventional sequence from the commercial textbooks where we begin with structure of the atom, introduce the idea of the mole, and then transition into stoichiometry. And then there by topic 5, we're into reactions in solution and molarity. And then with topic 8, gas laws. Eventually we move into the thermodynamics, 9 and 10. The properties of light leading into periodic trends, so that sequence, and then we finish the course with Lewis structures, molecular geometry, polarity, and some of the models of bonding in molecules. Now, each of these topics has a 2-letter code afterwards, which we're going to be referencing, but there's only a couple that I really want you to pay particular attention to, which is mole concept and stoichiometry, MC or ST, because I'm going to be referencing them a few more times. Now, to look at where at-risk students are struggling, one of the things we had to do is come up with a measure for it, and we ended up relying on Cohens D. So I want to unpack this a little bit. The first thing that we did was we took every assessment item or test item and assigned it to a topic. So with our code list, we were able to say this assessment item is measuring mole concept or something like that. Then we solve for the percent correct by topic for 2 groups. The first group is what's abbreviated as NAR, but pretty much anyone in the top 3 quartiles of Math SAT. And the AR, the bottom quartile, which is our at-risk students. We solved the pooled standard deviation by topic just to get an idea of what is the variance on these items, and then finally solve for Cohens D. So we have this formula for Cohens D, and what we have is the average for the non-at-risk subtracted by the average for the at-risk. And what that means is a positive value means that the at-risk underperformed. This would be a concern for us. This would be a sign that there's that differentiation between these 2 groups. And a negative would actually be the opposite of that. That means the at-risk students overperformed on that particular topic. And Cohen provides some criteria in terms of evaluating what those different effects might be. And so 0.2 would be small, 0.5 would be medium, and 0.8 would be large. And jumping into the data, this is what happened with 1 semester. So we took all of the test questions that happened during that semester, encoded them, as I said, and then created their different at-risk score correct and the not at-risk score correct and made Cohens D. So the y-axis for this, which should be labeled but isn't, is Cohens D, and the x-axis is the topics. There's a lot to this diagram, even though it's just one pretty blue line. So let's unpack it a little bit. If we start right here, what this would be interpreted as is for structure of the atom, the difference is 0.6, which means the at-risk students underperformed by about 0.6 of a standard deviation. We see kind of a consistent trend throughout, where they all tend to kind of coalesce around 0.5, so about a half standard deviation difference between these two groups. But we also start to see some local maximums, and one that I wanted to point out right here is stoichiometry, which is nearing that 0.75, so it's nearing a large effect size between them. The other thing to point out is that we see that they're struggling consistently across all topics. If we go to the next semester, the local maximum again at stoichiometry, this time it's above 0.75. For mole concept, we saw it at 0.75 as well. And like before, we see this kind of struggling throughout the semester, but we do see those two local peaks. The ensuing semester, spring 17, this one is a little bit more, well, a little bit less in terms of value on that Cohens D. So the highest one here is 0.5. Again, it's stoichiometry, but the difference isn't as pronounced as we've seen in the past semesters. And we did see kind of an interesting tailing off as they get toward the end when you start seeing things like Lewis structures, molecular shapes, valence bond theory. So one of the things that we were interested in beforehand is, would it be the topics that primarily dealt with math? And so when we start seeing that tailing off of Lewis structures, molecular geometry, those kind of things, we start to think, well, maybe it is the math. Maybe that's what this test is really telling us about. But there's another kind of way of thinking about it, which Math SAT could be seen as a more general cognitive measure, one that is describing a variety of skills. Some people have talked about it as a measure of high school preparation in general. I want to go to the next semester now, and that mole concept and stoichiometry have reappeared. One of the things that doesn't show up on this, because the number of items wasn't always there on each of the test assessments, we only did ones that were 3 items or more showed up, but we did see it on some of the interim, is things like properties of light, those kind of things. They did not have those local maximums. So when we explored that and thought, you know, if it was just the math, properties of light is very math oriented, we didn't see local maximums there. So it didn't seem to be just the math. So finally, when we average together those 4 terms, this is what it looks like. The stoichiometry peak maintains, which is what we start to expect because we start to see this in each semester. Mole concept also has a slight maximum compared to some of the rest of the topics. So it starts to form this hypothesis that it's mole concept and stoichiometry are the concerning ones. So first, that would be, as I said, our hypothesis. We followed up a little bit from there and tried to be a bit more thorough, make sure that we were, you know, not just finding a small signal and making a big deal out of it. So tried to look at it with other lenses, tried to see if we could discredit it in some ways. And one of the ways we looked at that was the missing data. In our sample, 60% of the students took a Math SAT, but another competitor is the ACT, and it's kind of a similar setup. They take it in high school. It has a math subsection. And so we looked at the students that were missing SAT. The ones who missed Math ACT, they had the same relationship. So it really started to see that these aptitude measures were identifying students that would then later struggle with mole concept and stoichiometry. And I mentioned earlier that these measures have been thought of as a proxy for high school preparation. And I think it's a bit beyond coincidence that we often expect that high school preparation would prepare students with topics like mole concept and stoichiometry. So when those students arrive at the university with a lower score, they may not have had an adequate preparation in these 2 topics. And I would also argue that the way we teach general chemistry, where mole concept and stoichiometry happen within about a week or 2 weeks, it may not be enough time for students who are missing that background to really catch up. And so that would be something we have to consider in our curriculum design. The other thing that we started to see is that later topics include assessment items that rely on mole concept and stoichiometry, and they also feature high differentials. So these are 2 examples. I'll let you take a look at the assessment item at the top for a few seconds. So this was coded gas law. Part of our coding scheme was that wherever the topic would have been introduced, that's where it received the code. Put another way, the latest in the sequence where this assessment item would have been placed was responsible for the code. So this was under gas log because you needed to use PV equals nRT to solve this problem. But it also relies on mole concept in that you have to know the formula for molar mass and be able to pull that out from the information you get with the gas law. Take a look at the second question now. And so this was classified as a molarity type question. It's one of the first where they have to use molarity in their calculations, but it's also a stoichiometry question where they have to find the moles of one chemical species from the moles of another in a chemical reaction. Now, for both these assessment items, there's some numbers below that. And where it says P, that is the percent correct overall. So we see 78 and 61% for these two items. MD is the mean differential. So that was the actual difference in percent between these two groups. So you see 25% in that top number. So it might be the case that the non-at-risk got it right 85% of the time and the at-risk got it right 60% of the time. Quite a large difference, really, if you were looking at percent correct for these two groups. And it really kind of puts a bit more of a face to it. And then same with the bottom number, that 30% differential. So one of the things that we're starting to see is that these later topics, even though they don't have as high a differential, when we pull mole concept and stoichiometry out of these later topics, the differential is there. There's one other aspect that we looked at was that not all at-risk students struggled with mole concept or stoichiometry. So some of them actually succeeded on these topics, and we wanted to understand their experiences as well. So they were labeled risers, and that was operationalized as had they scored 65% or better on either topic. It didn't have to be both, just one or the other. And so we enacted a similar kind of setup and same kind of Cohens D formula, but the difference here is it's not at risk minus the risers. And a positive value means the risers underperformed. A negative value means that they overperformed. And so we were able to come up with what their differentials by topic look like. And one of the things that we found is that the difference is quite stark. Here the numbers follow into the negative line, which gives us an idea that they're overperforming the not at-risk students. So within the at-risk students, there is this subset of students who have succeeded on mole concept and stoichiometry, and they are doing just fine in the course. They have no differential performance. If anything, they're a bit overperforming. And I kind of discount the mole concept here and stoichiometry numbers because that's how we define them. But later throughout the course, we don't see any of those indications that they're going to struggle any differently than the rest of the cohort. So one of the first implications from this in terms of a teaching implication is that stoichiometry and mole concept have those high differential performance, and we're starting to get more confident in that now that we've looked at it from a few different lenses. So we would advocate for some evidence-based instructional practices for these topics, and fortunately the literature has lots of examples of that. I've pulled a few of them here. And so Kimberlin and Yuzerski published an article that developed inquiry lessons for high school students and evaluated them with a pre-post design. Over there on the right, Davidowitz and company, they had done a very interesting instrument where they had students create submicroscopic diagrams for understanding stoichiometry. And at the bottom, there is Evans, Herein, and Leinhart, which had done an online introduction to mole concept and stoichiometry and evaluated that as well. So from a teaching perspective, these are three different techniques, and there's an evidence base to show that they were very promising in terms of promoting success with mole concept and stoichiometry. And so I think that considering them in terms of your own instruction would certainly be worthwhile doing. But from a research perspective, I'd like to add in the second implication that when we're looking at pedagogical effectiveness, we should consider equity. We should look at differential impact on groups of students. So it might be the case that you enact something and student performance overall goes up, but are these differential performances being maintained, or are they even growing? And that would certainly be something worth being concerned about and paying particular attention to. So that's the first study, and I would like to take a quick break for questions. I'll turn it over to Michael.
Great, thank you. Yes, so questions are flowing in, so I will do my best to try and get through them in the time available. Renee asked, I guess this is a US sort of focus question, where is the SAT data based on the SAT percentiles or the incoming USF student body quartiles? I assume that makes sense to you.
Sure. So the SAT is a nationwide test, and they publish what the national quartiles are. But we created these based off of the cohort that was entering into the schools. So when I say bottom quartile, we took all the students in our cohort and demarcated them by quartile.
Okay. Do students, all your students have a background in chemistry? Did they do AP chemistry or?
So their background in chemistry is varied. Our school certainly has some students who have taken AP, which is a version of college prep in the US. So they're in high school taking the equivalent of a college course. A lot of those students have the chance to test out of it as well. But what we really do see is a range, and we've got students who may have had only one semester of chemistry in high school that would enter.
Okay. A question from Miami University CER, which I think relates to your research implication. How many different instructors are there for the course, and do the teaching styles differ, and how do you observe differences and so on? So I guess this issue around how do you know that everybody's getting a consistent message, I suppose?
Sure. So within our setting, fall semester typically has about 6 or 7 different classes running. Spring semester tends to have about 4 or 5, probably 4. One of the things that happens before the semester begins is we agree to a common syllabus that does have the content coverage, how much time, and when the exams would be, those kind of things laid out. As far as teaching styles go, in terms of pedagogy, there really isn't a great deal of difference. The peer leading part that is in place is a mandatory component for all of those classes. But obviously, the person that walks in the room is different. And so they're going to have a different style. They're going to use the clicker questions differently. How many different teachers that we have? Each semester, we probably had 4 or 5 teachers. So across these 4 semesters, we probably had about, I would guess, around 8 to 10 different teachers that were teaching one of those classes.
And in regards to the fall and spring semesters, Nikita is asking, do the students in the spring section primarily consist of students that have previously failed and are retaking the class, or are they a new bunch of students?
So that's a great question, and I haven't looked up that number exactly. One of the things that I can point to is that our failure rates really are not that high. They usually hover around 10% or lower. So it's unlikely that the spring semesters were comprised a majority of students who are repeating the course. There's probably an element of that. We do notice that there are some clear differences between fall and spring, but I don't think that it comprises any large majority.
The other thing I noticed, and maybe this is a completely non-statistical analysis, but there seemed to be in all your diagrams a general drop as the year went, as the list of topics went on. Is there an issue here just around gaining familiarity on topics? In other words, I understand that you talk about specific topics and they're difficult, but it's just a general issue about becoming familiar with university that helps the at-risk students reduce their differential, if you know what I mean. Have I make myself clear? So in other words, it seems to be, for me, when I look at data, there's always a slight sort of, although it's oscillating around 0.5, it seems to just sort of curve down as you go across these topics. Is that due to the topics themselves, or is there something about the students becoming more familiar with university?
Yeah, we do see that in some of the semesters. The spring semester, spring 17, it was pretty clear, and I can navigate back to that, I think, pretty easily. So here we go. So that had that decline, and I think that was pretty evident. When we averaged by term, it was a little bit more of a plateau-ish instead of what we saw in spring 17. As far as differentiating, I think you've got a really interesting question. It could be familiarity with the assessment practices, with the model of instruction, and with being a university student, or it could be the topics, in particular valence bond theory and how we assess that. It might be one of those where it's very recent, they only see it on a final exam, and so they're able to succeed in that a little bit more.
Okay. And then one final question, Renee, asking, I think, again about the SAT again. So the SAT is intended, and she has inverted commas, to be a predictor of success in college. Your data seems to support that if it's based on national quartiles, although that doesn't address the issues related to equity of experience for admitted students. I'm sorry, Renee, I'm not sure I understand the question. I might come back to that. I might ask Renee to clarify that, and we'll come back to it at the end. So I'll pass back over to you, and you can continue with the seminar.
Sure, thank you. And thanks everyone for all those great questions. The next study I wanted to talk about is looking at student study habits. So this is going to be a kind of synopsis of a couple research studies that we had done, one of which is directly related to the same group of at-risk students. We'll begin by defining study habits. And so the definition that I wanted to use would be the frequency and type of any activities that students do oriented toward learning class material outside of class. And kind of with the caveat that there should be things that are in addition to required activities is what we were looking for with study habits. A little bit of background. So what I've got on the left here is a kind of snapshot of a meta-analysis that was published on study habits. There's been an awful lot of work. This one came out in 2008. There's also been some like 2011 as well, but a lot of the findings seem to be consistent that study habits are related to academic outcomes. They're independent of cognitive measures like SAT scores. And so that kind of cuts down the potential idea that they're confounding variables and that you're not really looking at study habits, but it's just you're looking at better prepared students and they just happen to exhibit better study habits. Instead, it really seems to be that even for students who come in with lower measures on these general cognitive measures, the study habits still matter for their academic outcomes. But one of the things in this meta-analysis that we noted was that there was no measures of specific science performance. So a little bit more in terms of how they measure study habits. There's different ways to do it, but two of the most common are inventories, one of which is called the LASSI, which I really like to say, the Learning and Study Skills Inventory, and the other one is Survey of Study Habits and Attitudes. And so one of the concerns that I might have, though, is that when you get a survey like this, oftentimes they're asking you to reflect. You can imagine being a student and you're in a class and you get a survey maybe halfway through the semester or something like that, and it says, you know, how many hours a week do you read the textbook? And with that, you're probably going to be a little bit flummoxed. You might just make an estimate like, well, you know, I like to read some, maybe 2 hours, or I think you're going to make an estimate there. And I think it kind of ignores the variation that could happen throughout the semester, because it probably is that, you know, if you had a very big test coming up, you might have read a lot. And then on another week where the class is a little bit less assessment heavy, maybe it got put on the back burner for other courses. In terms of chemistry specific, there really does seem to be this growth of research interest and study habits, and it's exciting to see. This kind of quick synopsis about some of the studies that have happened recently. So Richards, Babb, and Jackson found male students were more likely to procrastinate studying. Next, Lee et al., upper level students were more likely to cite higher level studying techniques, but it's kind of hard to demarcate when you're comparing upper level and lower level students because we know attrition is not random. Next, Cook et al. Found a one-day lecture on study habits led to improved academic performance. So they had a one-class lecture after the first test where they presented a study cycle and had students make a voluntary commitment to enacting some elements of it, and found that the students who did that performed better in the course. And Bunce et al. Has done a couple papers recently that found that successful students use deep study approaches, and deep study approaches usually means they're striving for meaning. They're not striving to memorize. They're trying to make connections within the content. They also found that these students adapt their approaches more, that they would change their approach based on the type of assessment. This is something I find really interesting, and I'm going to come back to by the end of the seminar. So if I had to summarize the research literature, study habits likely play a role in academic success. They may be malleable. We do see evidence that students can change their study habits during the course of a semester. And that those single admission surveys, I kind of hinted at some of these problems before, that relying on retrospection, they also presume that study habits are constant. So one of the things we wanted to look at was, could we look at study habits a bit more proximal to when they were occurring? And we found a methodology that let us do that called experience sampling method. And in short, what you do is use technology to facilitate multiple measurements. And to give you an early idea of how this happened was, in the 1990s, people had pagers, and what you can imagine is that before everybody had a cell phone, they actually carried around this little thing, and it would just show up a phone number sometime telling you that you needed to go call that number. So researchers started using this, saying, okay, we'll put pagers on our participants, and we will page them, and then they could write down in a log something about what they were doing, be it an interest in, you know, psychological constructs, like did you do something good today, or how do you feel today? And From there, the measurements occur in a participant's natural environment. When you think about some of those examples that I gave, did you do something good today? You don't want to go into a research setting, you don't want to go visit a psychologist's lab and then have to think back about those things. Instead, it would be much better to say, yes, I helped somebody to their car or something like that the day it happened. It does rely on participant self-report, which is an advantage and a drawback. One of the things that we're thinking about here are cognitive measures like study habits. And so self-report does seem to be somewhat necessary when you're thinking about study habits, because the truth is, even if you could follow somebody around 24/7, which would be quite creepy to do, but if you could do that, just because they happen to have a book out and the page is open, that doesn't necessarily mean they're studying. I mean, they might be focused on other things. They might be thinking about something completely unrelated. I think you really do have to rely on the participants' evaluation of their own activities over whether it constitutes studying. So a little bit about our setting. It's the same setting, but the topic sequence has changed a little bit. This is what's colloquially called the atoms first approach. And so here it begins with quantum numbers, electron configurations, periodic trends as a first exam, then into bonding with things like Lewis structures, molecular shapes, and then finally a bit more of the application with gas laws and thermodynamics, and then followed with intermolecular forces and solutions at the end of the semester. And so we wanted to do a methodology where we were going to use experience sampling methods, and we went and recruited from 3 general chemistry classes. So there were 670 students total in this recruiting class. And we told students that we were going to be text messaging them to ask about their study habits, and if they agreed to participate and responded to 80% of the messages, they would be in a raffle for a $25 gift card. They had a 5% chance of winning because we didn't really have tons of money to allocate for this, and there are hundreds of students involved. So our diagram on the right got a little bit chopped up here, but I think I can unpack it. The yellow color represents people that we did not recruit. So there was one class that we did not recruit because the instructor was part of the research team and we didn't want that to appear coercive. The blue section are students who agreed to participate. So we had 301 students agreeing to participate. And the green section were recruited, but they did not participate. So what we did is that we told the participants they'd receive a text message twice a week, so 28 times over the course of the semester. The question would remain the same. Have you studied for Gen Chem 1 in the past 48 hours? If so, how did you study? We asked them to respond within 12 hours, but we counted any response that came before the next message that went out. But most of the messages did come in within the 12-hour time frame. Most of them actually came in within a few hours of sending out the message. And one of the first things that we weren't sure about was the feasibility of this approach, because I hadn't read a whole lot about people trying something like this, and there was logistics to be concerned about in terms of sending out mass text messages and using software to do that and all those things. So one of the first things that we did was try and get an idea for what did we get? And so we actually got a lot of responses, 4,775 total responses. For people who are interested in this approach as a research tool, that 80% threshold might have made a difference. We saw more people responding to at least 80%, which are those bars on the right, and that's 23 of the 28 messages or more. We also had about 10% of our sample that never responded to a message, and that could be that maybe they provided an incorrect phone number, or maybe they saw the first couple of messages, thought they were annoying and set it on block. We don't know, but we did lose about 10% from that. So I do want to talk quickly about how do we have any evidence for the validity? How can we trust the messages that we received? And so I'm going to talk about a few of the things that we did to kind of explore that. One of the first is that we were concerned that the people who agreed to participate might be unique or different from our overall cohort. So this table kind of compares the people who participate to the people who didn't. And what we found is that the differences weren't that great. Our gender difference was a bit that we had a 6% difference where more females had agreed to participate than non-participate. Same with underrepresented minorities. We had a difference of 5% there. But overall, these effects tended to be small effects. So we thought that our results could be generalizable to our overall cohort of Gen Chem students at the setting. Next, we were concerned about content validity. So thinking about content validity, one of the first things that we did was we created a code list, and we had 16 different study habits, which coincidentally was the same number of topics from the previous study. So some reason we gravitate towards 16. But we came up with 16 different study habits. And so one of the things we did was code each response, and many of the responses got multiple codes. So one example response is, yes, the back of book problems, reading the chapter and doing the online homework. So we coded that as textbook, practice problems, and homework. So 3 codes were applied to that response. And we did some inter-rater agreement. We found 94% agreement between raters. And one of the next things that we're able to do is classify what code showed up most frequently. So of the 16 codes, these 6 showed up most frequently. Did not study was the most frequent code. And so that kind of gave us some credence that when we were worried about socially desirable response patterns, that people would just tell us what we want to hear. They're going to tell us that they studied all the time. Well, actually, close to half the time they said that they did not study. Another thing that was particularly interesting about this is I mentioned earlier that there's this peer-led group session that happens every week. And we thought that that would promote naturally students studying in groups, but they really did not respond much with that. In fact, less than 5% of the responses indicated that. It was relatively infrequent. Another thing that we're able to do, before I move on from that, notice also online homework was 14%. So earlier I defined study habits as being students working on things that were not required for the course. But a number of students pointed to the online homework as examples of them studying. And so that really kind of changed our thinking for it. It wasn't expected at the time because it was a required element of the course. One of the things that I would mention is that in practice, over 95% of the students actually did the online homework. So we had very high success rates on those metrics. It's just 14% of the codes had indicated that they'd done it. We think many of the students did the online homework, but never considered that studying, perhaps as we did. So from there, we were able to come up with a percent of students who reported studying, and that's what this blue line reports. And on the x-axis is their calendar dates throughout the semester. And at first, this seems kind of scattered and random. We notice that there's a baseline here around 30%. So what we found is that those peaks coincided with the dates of major exams. And so that gave us some credence that when they were reporting studying, it probably matched what we expected, that there was these general peaks right when the exams occurred. And so one of the next things that we were interested in, so study habits to academic performance, we wanted to know, did these study habits relate to academic performance? And one of the first things that we found is that we first wanted to filter them. We wanted people who responded to at least half the inquiries. So we had 28 inquiries, and we looked for people who responded to at least 14, because we didn't want to infer much from someone who might have answered 2 or 3 prompts throughout the semester. And overall, the correlations with performance really weren't that high. The highest correlation we found was 0.14. But one of the things that we started getting interested in is maybe there's some groupings of study habits that did matter. And so to explore that, we used cluster analysis to see if some of the study habits occurred concurrently. And what cluster analysis does is it takes the data and it looks for patterns in the data. It looks for students who seem to respond in a similar way. We ran the cluster analysis on that filtered students who responded at least half the messages. It actually separated them out into 3 evenly represented groups. Now, there's nothing about cluster analysis that indicates it should do that. We could get one group that's 90% of them, another group that's 5%, another that's 5%, and here we got about a third each. Unfortunately, we didn't really have the sample size to do some of the things like split half reliability to make sure that these clusterings were consistent. But what we found was somewhat interesting. So one of the things that I want to do is kind of highlight where they were relative to the overall percent. And so I bolded the numbers that are at least a half standard deviation above the overall percent, and I underlined the numbers that are at least a half standard deviation below the overall percent. And that helps give us some context for what these clusters represent. And so cluster 1, 67% reported did not study. So 2/3 of the time they said, no, I did not study. And that was a lot higher than our overall of 42%. So with those values, we were able to come up with labels for these clusters. And so we labeled cluster 1 as knowingly did not study, cluster 2 as studied additional components, and cluster 3 as they saw mandatory components as studying, because this group seemed to report online homework a bit more than the rest. We also saw this group, and overall, people kind of went away from reporting online homework as the semester progressed. It seemed to be something we saw a lot more early in the semester. So we have these 3 clusters, and as I mentioned, we're still interested in how does this relate to academic performance. So with the 3 clusters, we can see how they did relative to each other on items like the final exam. Before we jump into that, we looked at their SAT scores as well, and there really didn't seem to be much difference between them. We have a survey that was handed out that was about deep approaches versus surface approaches. As I mentioned before, deep is about making connections. Surface is about more closer to memorizing the content. And when we do a test for statistical significance, what we found is that the cluster that reports studying regularly throughout the semester, they did better on the final exam compared to the other two clusters. And this was with really no advantage in terms of the SAT score. So if anything, they actually had the lower average SAT score compared to the other two clusters. So from there, I'd like to return back to the equity framework. So we've got this indication of study habits. We have an indication that they seem to relate to academic performance. But what were the study habits of at-risk students? So one of the first things that we did with the same data set was we demarcated students again from bottom quartile as the at-risk and the not at-risk, the top 3 quartiles. So our sample size goes down a little bit here as well because these are students who had SAT scores and not everybody did in our sample. I kind of first want to point your attention to the yellow box. So there's 3 metrics there: attendance, homework, and study percent. Attendance is how many times did they attend the class, and that's from their clicker usage. Homework is what was their average score on the homework. And as I mentioned, a lot of students did very well on that. And then study percent is what percent reported, or how often did they report studying? How many times did they say yes, they studied, over how many times did they report yes plus no? And so what we see is the at-risk students, attendance to class slightly smaller, the homework percent slightly larger, the study percent quite a bit different. So we see this difference of about 15% between these two numbers, about a half standard deviation. Now take a look at the orange box. These are their test scores. And what we find is that the not at-risk students consistently receive higher test scores or earn higher test scores on these tests. One of the reasons I point this out is because one of the gut reactions some instructors might have to this is that maybe the at-risk students just aren't studying enough. And I've certainly heard that from some people. They may not use those exact words, but they often attribute student struggles to whether or not they study. Well, here we found a group of students who actually report studying more than average, but they're still performing worse in the course. And there's other literature that seems to support this, that it may not necessarily be time on task for studying that matters, but it might be more the quality of studying. And so we got to be a lot more interested in that. One of the ways that we started looking at it was maybe the relationship between studying and performance in the course depends on SAT scores. So this graph looks like it got a little bit truncated in terms of the legend on the right. But in short, the blue line is a math SAT of 650, which represents something close to the top quartile. The green line at the bottom represents a math SAT of 500, so that's actually in the bottom quartile. And one of the things we found is that there actually is an interaction when you run a regression on this, where the percent of studying seemed to make a much bigger difference among the at-risk students than it did for some of the non-at-risk cohort. Every time I present this, there's always some concern and some interest, and I completely understand it with that blue line, where the percent of studying actually indicates a lower performance in the course. To explain that, it's really just hypothetical. I don't really have a good explanation. Well, I think I have a good explanation for it, but I don't have any evidence to support or dissuade me from it. What I believe is that these students who enter with high SAT scores likely are familiar with the chemistry content, and many of them can succeed in the course without regular studying throughout the course. They've seen a lot of this before and they've succeeded on it before. When students of this high SAT score report studying all the time, it might be in response to an unsatisfactory performance on some of the assessments. So that might be what we're witnessing here, is that whenever those students report studying, it's not that that studying hurt them. It's not that that's a causal relationship, but instead it's more just symptomatic of the fact that they aren't happy with their performance to date in the course. But again, I don't really have any evidence one way or the other regarding that. While we were working on this, we started interviewing students to learn a bit more about, we started interviewing at-risk students to learn a bit more about how they studied in the course beyond what they told us in the text messages. And as we were doing that and analyzing our interviews, this great paper came out, and I really wanted to unpack it a little bit to help understand a bit more about what we're going to see in the interviews. So Sinopuelis and Stacy, and I'm sorry if I mispronounced that name, came out with an article in the Journal of Research and Science Teaching. And what they did was they had a group of students in general chemistry that 3 times during the semester they interviewed about their study approaches. And they created these levels of what they called a learning approach framework that describes different ways that students were studying, and it's a hierarchical level. So level 1 was gathering facts, where students were really just trying to collect together information. Level 2 was learning procedures, and you might view this as kind of memorizing, practicing the same problems, those types of things. And both of those kind of map onto the surface approach that I mentioned earlier. Level 3 is confirming understanding, and that's a really interesting use of words, because what these students were doing is that they had formulated their own understanding, and they were actually looking for testing it with others. So these might be people who come up to a group of students, if they're in group work, and saying, I think it's this way, what do you think? Or they might be approaching their instructor in the office hours and saying the same thing. They might be saying, I understand the relationship between temperature and vapor pressure, but how do you explain this? So they're testing out their own understanding. They're seeking feedback on it. Level 4 is applying ideas, taking ideas to novel situations, and they didn't really see a lot of evidence of that in the interviews that they did. The other thing that kind of contrasted it was, I told you level 3 was confirming understanding. Level 1 and 2, oftentimes this is characterized by students seeking understanding from others. And so for me, this was actually so telling for my own instructional practice. You've had students come into your office and they would be struggling, and they might say, I don't understand. And I think as an instructor, what do you do? So I would try and clarify, you don't understand what? And they might say, anything about chapter 13 or anything about this. And you're kind of at a loss there. So you find yourself kind of going back into class mode and teaching the subject again. But they've already been to class and you've already had this. It's not going to have a different impact is kind of what I came to realize. And with this framework, I start to see that those students are in this level 1 and level 2. They're seeking an understanding. They want somebody to give it to them. They're hoping to come to office hours and that I would hand them an understanding, but it can't work that way. Understanding is always a personal developed thing, and it actually works best from testing your understanding with others. So I'll come back to that when I get to implications, but I wanted to kind of preface the interviews with that. So we interviewed 6 students, and so we gave them pseudonyms. And one of the things that we found is that they kind of fit into these quadrants, one of which was how frequent did they study, and that's based off the text messages. And the other one is, do they enact those surface level approaches or deep level approaches? And so that's the vertical axis in this quadrant. I'm going to begin with the bottom 2 quadrants, Jack and Ellie and Lucy, and they were using the surface approaches. And so here are some exemplar quotes from those 2 students, and I'll let you read them through. So some of the hallmarks of this is these are some exemplars of students that were seeking understanding from others. As we see with Lucy, not a textbook person, I don't understand what they're trying to say. With groups, you get help if you don't understand something. So not that she's formulated an understanding, but that she's seeking it from others. And then on the bottom left, we get some of the indications of gathering facts, copying some of the notes just to help get a better memory of it. The other surface characteristic, that kind of lack of long-term retention. I don't really remember like what it was in Gen Chem 1 we learned. So these interviews happened shortly after the semester had closed. It was a fall semester at the beginning of spring. Now I kind of want to unpack the top 2 quadrants. So that's what we see here. I'll let you read through these. And here we start to see evidence of that testing the understanding. I would ask my TA, if I do it this way, am I right or wrong? I prefer to study in groups. I end up knowing more, so I tutor. So they're also explaining it to their peers. The homework is my self-quiz. They're getting that feedback on their own understanding. That's how they view their studying habits. And so one of the things that we did was look at their performance at the end of the course, and this was their final grades in the course. And one of the things I want to unpack about this is particularly about Mary. So Mary had the 2nd lowest SAT score of the entire cohort, but she finished the course with an A-, and it was clear to understand why. If you looked at her study habits throughout the semester, her text messages clearly indicated an evolving, robust pattern. She continually tried different things, but her interview really validated that for us, and that she would even pull back through her text messages and explain them to us in a very reflective way. So we really do think that study habits are a way that at-risk students can succeed. One of the unknown questions left is it frequency or quality? And so to wrap it up with some implications from this study, one of the things that we would advocate is regular studying and formulating understanding would promote success for at-risk students. Now, that's easier said than done. Some of the ways that might promote this would be to consider regular assignments that students would be completing and getting feedback on. More frequent tests is one of the things that we're considering, whether that's logistically possible in our setting. But I also add in opportunities for students to present their understanding. So I had the anecdote about my office hours and students who come in during them. One of the things that this work has changed for me is that when I work with those students, I challenge them to try and write up a one-page summary about the chapter, and not working problems, but describing the big ideas from that chapter. And I offered that if they do that and send it to me, I'm happy to provide them feedback. I'd love to do a study on this, and I'm still considering enacting something similar to this, and looking for ways to support doing that. But anecdotally, whenever I've done it, it seems promising. So that does match the learning theory that it's when students are able to formulate their understanding and sharing that they're going to progress a lot better. And I think that's particularly true for at-risk students. One of the other things that I think is particularly interesting is that I mentioned earlier, students change their study habits during the semester. And I think that more research is really needed to understand how we can promote positive changes in those study habits. I want to give an example from our own data. So this diagram, each circle, the size of the circle is the number of times they said that particular study resource, and the lines indicate overlap. So solid line means that it's a high degree of overlap, and the more dots, the less degree of overlap. And the percentages are based off of the percent of the smaller circle. But the reason I bring this up is look at the changes throughout the semester, where we see exam 2 getting a lot more networked, and 1 and 3 a lot less networked. And then the final exam, which was cumulative, far more networked than either of the others. So what really drives these changes is the nature of the content. Exam 3, for example, was very math-oriented, and that might have driven students away from some of the resources like the textbook. And the final exam was cumulative. Maybe that's what caused for all of this multiple resources being used. But I know, or I'll put it this way, I'm convinced that they are changing, and I'd really like to understand a lot more about why they're changing, because I think that's important for us to be able to promote success. So I'd like to close with some acknowledgments. First, all the participating students and instructors. We obviously couldn't do any of this work without them. Lee Yad did all the work related to study habits. She's currently a faculty member at CSU Northridge. Vanessa Ralph did the work on the by topic performance for the at-risk students. NSF also supported this work, so I clearly want to acknowledge them with their ubiquitous disclaimer. As far as references go, here are the references of the studies that I presented. So if you'd like to learn more about them, but please also feel free to contact me if you'd like more information about them. I'm always happy to talk about this work. And I'm going to close with a thank you to Michael for putting this all together. I think it's a great idea. I'm so happy I've been able to participate in it. And also thank you for joining us today. I hope that you got a lot more questions. And here's my email address if we can't get to your question today.
Thank you very much, Scott. A really interesting, fascinating overview. So there have been a lot of questions. Unfortunately, when we had that technical glitch, and I'm sorry to you that you had to deal with that, I was also kicked out of the room, but I have picked up on the questions. So I'll just go back to the one that I wasn't able to represent Renee very well, but essentially she was asking, let me just get it out here again, that SAT, because SAT is intended to predict success in college, she's sort of saying, kind of as an opening gambit, well, are your results that surprising in the first half? So SAT predicts success, you're finding students with lower SAT aren't as successful. Is that surprising?
I don't think it's surprising in the sense that they're not as successful, and that's not really, I think, what our intent is, but really trying to understand why they're not successful. And so, you know, if we take the approach that these are just general measures and these students may not be ready for the course, I don't think we're ever going to make a giant difference in terms of our performance that we see overall in our setting. I find this particularly interesting because students who enter with the lower ones, they have that higher risk of not succeeding in the course. And so if we can understand the nature of their struggles, then we can make interventions that are designed, that are tailored based on that evidence. And we could actually make a big difference with a group that needs it the most.
Okay. Your neighbors in UCF are wondering on slide 39, which is the slide with the content validity where you had the burgundy lines.
Yes.
There were some peaks that didn't associate with an exam, and do you have any idea what was happening there? Why were you seeing some? There were slightly smaller peaks as I saw them, but there were peaks. Yeah. Oh, well done. Yeah.
As far as what's happening there, I'm not really sure. The one thing that I can point out is the plateau that happens after the second exam that coincided with right after spring break. And so there was that kind of lull there. But why we saw those kind of blips up to 75% periodically, I'm not really sure.
Regarding the method, were the messages sent out at the same time each week, or were the times varied?
Sure. So we did it randomly. We told them that they would receive the messages only between 9 a.m. and 9 p.m., and we would do it on 7 days a week. We did tend to avoid major holidays. We didn't send messages out during spring break as well. But other than that, we didn't want to bias it by only looking at weekends or only looking at night or anything like that. We were random.
Okay. And then there's a query about Ava's quote, which I think is slide 54. A question asking, how is this quote representing deep understanding? The questioner is wondering or thinking that it seems to just be saying the book has done the understanding for that student.
So for me, the textbook's a bit different. When it's students receiving understanding, they tend to be relying on other students doing it. Whereas I think the textbook, if you believe that you've gotten understanding from the textbook, it's a study resource. And so you felt from that you have an understanding. We interpreted that as an exemplar that the student now has an understanding. And it's also a sample quote in the sense that with the overall quotes from it, and in the paper we've got a bit more, but the overall picture for it showed more indications that Ava would do that. And we got that other quote there. I'd ask my TA, if I do it this way, am I right or wrong? So that's why we ended up with that classification. I could see where that one quote out of context, though, might fall a little bit short of that.
Yeah. Just back to the peaks, Michelle Richards-Babb, who you cited, obviously, is here, and she asked whether those peaks might be due might be associated with when online homework assignments were due.
That's an interesting hypothesis. It certainly could be true. We could go back and take a look at that.
We're fascinated by these peaks. Did a change in study habits over the semester have an effect on the final grade?
That's a very good question, and I don't really have a good method for exploring that currently. So when we think about the changes in the study habits, and I can go back to the diagram, so this represents about 110 students, each of which replied to the message that went out right before each exam. And this is just the resources that they used as they were leading up to that exam. We could try and characterize the types of changes that happen with this, but I need to think a bit more about how to do that because it's not entirely evident. We'd probably need to come up with a coding scheme that would be able to let us say, these changes were in this direction.
Okay, and the final in your rapid quickfire, sorry, I'm firing at you, question is from the Savine group. Did you notice any difference? I'll read it slowly. Did you notice any differences in their approach between the student with surface approach and low frequency and surface approach with high frequency?
It's a really good question. Nothing's coming to mind except I do remember, because it's been a couple years since I looked at the raw data from this project, the surface approach low frequency seemed like students who were disengaged from the class might be one way of describing it. They really didn't have a positive affect toward the class, and I think it kind of felt like there was elements of guilt in it, but there was also this certain amount of, I really didn't want to study for this, but I do when I have to. So that's explained that low frequency, and it was kind of like, and when they had to, they didn't really have a good plan for doing it in a sense that it was kind of like, I started working some of the problems they gave, but that was it. They tended toward unidimensional in that.
All right. Well, that was sorry for the bombarding of questions, but there were lots flying through, so I just wanted to make sure we covered as many as possible. So I'm sure you'll all join me in thanking Scott for a really fascinating talk, both in terms of the methods you've used. I really loved that study habits method. It's fantastic. And just in eliciting how we might be able to work on our own practice and consider our own teaching approaches. So thank you very much, Scott. And I will just highlight that we are now taking a break for Christmas, but we will return in January, and we're trying something new in January, where we will showcase two very promising researchers at their early career stage, Kinsey Bain, who's now postdocing at Michigan State, and Maya Popova, who's now postdocing at UNL. So they'll have two short half-hour talks each, and they'll be on the 23rd of January in the deep, dark winter of Edinburgh at 7 o'clock GMT. So I'll leave that flyer up, but I'll just sign off now by saying thank you very much to you, Scott, for a really fantastic webinar.
Well, thank you again, and thank you, everyone.
And I'll